In the third video of this playlist, we will look into register transfer level combinational design. And the expected learning outcomes from this presentation are listed here. So you shall be able to list the most common VHDL data types and to relate these data types and the operations that can be carried out over them. You shall be able to differentiate between concurrent and sequential statements in VHDL and to describe them. And finally, you will be able to explain what are constants and generics. So the data types are presented in table 3.1 of our book, which in this case addresses the data types comprised in the standard logic 1164 package. And this is the most common data types that we will use. So the standard logic 1164 package will mostly always be used in our designs. And you can see here that some of the operations that are referred here are not available for synthesis. So when it is the case that we want to synthesize an ether, for example, we will need to include a different package that we will see in a moment. But apart from that, if we wish to concatenate, for example, which consists of merging two bit streams, this is possible over the data types defined in the standard logic 1164 package, as well as comparing two values or seeing if they are different, and the various types of logic operations that we are familiar with. Now, when we want to do arithmetic operations like adding or subtracting, for example, or relational operations, then we shall include the numeric standard package into our design as well. And this package will enable us to carry out these operations over these data types: unsigned, natural, signed, or integer. Now, there will be cases where we will need to convert from one data type to another, namely, for example, the inputs and outputs of a circuit will be defined as standard logic or standard logic vector data types. But if the circuit is a counter, for example, then counting up or down consists of adding 1 or subtracting 1. And this means that we will, since the arithmetic operation requires the unsigned data type, for example, we will need to, in that case, convert from the standard logic vector into unsigned, which can be done by this statement: unsigned, and then in between brackets the original standard logic vector data type. We will see specific examples of typecasting or type conversion in a following presentation. Now, in what comes to the main VHDL statements that we will use, they fall into these two categories. There are concurrent statements and there are sequential statements. Concurrent statements, as the name indicates, execute concurrently, and we will see two types: the conditional and the selected signal assignment statements. Now, the sequential statements are encapsulated into what are called processes, and inside a process the various sequential statements are executed in sequence as indicated here. The process itself, however, is a concurrent statement that it executes concurrently with these other statements indicated in this slide. In the case of sequential statements, we will see these three types: the simple signal assignment, the if and case statements. And the pages indicated here relate to where these various statements are considered in our book. So in the first case, we will look into conditional signal assignments. And for this type of concurrent statement, as well as indeed for the others, we will consider as a specific example the priority encoder that is shown in this truth table. So a priority encoder is a circuit that considers a given number of inputs, in this case 4 inputs. So we will have input 4, input 3, input 2, and input 1, and the output will be the binary code indicating what is the highest priority input that is active. So in the case of input 4 being at 1, then the output code will be 100, which is 4 in binary. And if it is input 3, then we will get 011, which is 3 in binary, and so on and so forth, until when no inputs are active, we get the output code 000. So we can implement this priority encoder function using a conditional signal assignment concurrent statement, which has the syntax shown in this slide. So we will say that the output P code takes the value of, in this case, 100, when this condition takes place. That is to say, the highest priority input is at 1. Else, it will take this other value when the second highest priority input is active, else, and so on and so forth. Now this same priority encoder function, as we see in this other slide, can also be implemented using the other concurrent statement that we referred, that is called selected signal assignment. In this case, the syntax is shown in this slide. So we shall say that with input R, we will select for the output P code this value when any of these input conditions are met. If none of them takes place, then it shall take this value when any of these input conditions are met, and so on and so forth again. Now you might ask, when shall we use the conditional signal assignment or the selected signal assignment? Well, it's basically a matter of economy of representation, although they actually correspond to different hardware structures, as you can see in the book pages indicated where these hardware structures are represented as well. But in this case, it looks like the conditional signal assignment would be a more appropriate representation for the priority encoder. Now, if we move on to sequential assignments and start by looking into the simple signal assignment statement, actually the simple signal assignment can also be used as a concurrent statement, and the syntax will be similar, of course, but the semantics are different. Actually, if the simple signal assignment statements are used inside a process, as shown in the left here, then we know that they are executed in sequence, because that's what happens with the sequential statements encapsulated inside the process. And so there is no doubt that the last statement to execute will be the one that defines the value of C. So in this case, the final value of C will be given by A or B. However, if these two statements are located outside the process, then they will execute concurrently, meaning that we will have two parallel branches in our circuit, one of them allocating A and B to output C, and the other one allocating A or B to this same output C. In hardware terms, this might be represented as connecting the two gate outputs together. So we would have an AND gate and an OR gate, and their outputs would be tied together directly. Or, well, in most cases, this would be seen by the design tools as a design error, although it could actually take place in practice if they were outputs of the open collector or open drain types. Now there's one other important aspect to refer, which is the process includes what is called a sensitivity list, and the sensitivity list comprises all the signals to which the process responds. That is to say, whenever there is a change in any of these signals, then the process will execute. So any process will execute when any of the signals present in its sensitivity list change its value. Well, the second type of sequential assignment that we have referred is the if statement. Well, most of you will be familiar with the syntax of the if statement from the C programming language, for example. And what we see in this slide is how to use the if statement to again implement the priority encoder function. Well, it is important at this stage to call your attention to the fact that the sequential assignments, sorry, the sequential assignments are something that is completely different from sequential circuits. Sequential assignments is one thing and sequential circuits is another thing. Actually, in this case, we are using the sequential statement if to implement a combinational circuit, which is the priority encoder. Well, the else if and else statements are optional, so we could just have the and if. But building this logic function using a if statement is quite straightforward. So what we will say is that if the most significant input is 1, then Pcode output will take the value 100. Else, if it is the second highest priority input that is at 1, then Pcode will take the value 011 as indicated here, and so on and so forth. Finally, the third sequential statement that we considered is the case statement, and those of you that know the C programming language will also be familiar with the syntax of the case statement. Again, we are using the same priority encoder example to illustrate the syntax of the case statement. In this case, what we are saying is that case input R is, well, when any of these combinations takes place, then output Pcode takes the value of 100, which is the first line in our truth table. So all those input combinations listed here are those that have the most significant input at 1, as you see here. Well, if none of these patterns takes place, then we look into the case of the patterns which will define the second line in the truth table. And when any of these input patterns takes place, then Pcode will take this value, and so on and so forth. Now, one important thing to call your attention to is that the if statement and the concurrent signal conditional signal assignment statements will be equivalent if each branch of the if statement contains only a single sequential signal assignment statement. That is to say, in between the if and the else if, we might have several statements indicated. In this case, we have only one. So actually, this will be, if we go back to the conditional signal assignment, we will see that these two structures, the conditional concurrent statement and the if sequential statements, are indeed equivalent. However, if is a more general statement, since we can have several sequential signal assignment statements under each possible situation considered here. The same happens with the case and the selected signal assignment statements. And again, in this case we have only one statement included for each combination, so it will be equivalent to the selected signal assignment statement. But we might have more, so case is a more general structure. Finally, before concluding, I would like to call your attention to the fact that when we design any circuit that has a given number of bits, for example, it is convenient that we start by defining a constant, in which case if we say that constant n takes the value of 4, then if it is a counter or a shift register or whatever, we can simply use the constant n in the code. And if we later on want to change into an 8-bit instantiation, for example, then we simply change the definition of the constant. Now, a constant is defined inside the architecture body, but we might also define what is called a generic inside the entity declaration. So a constant is defined in the architecture body, and the generic is defined in the entity declaration. In this case, the generic is a more versatile approach, since when we instantiate this module at a higher level, we could redefine the value of n, which would override the definition that was given inside the entity package. Now, on the other hand, if we define the generic inside the entity, it will be seen as a constant inside the architecture. So if we do it as a generic, we will still be using it as a constant inside the architecture, but it can be overridden at a higher level if we use this module, if we instantiate this module at a higher level.